Hi, I'm Reverend Greg, and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. This time we'll look into creating a silhouette shader based on the player's position inside the room using the vertex attribute in position. As always, a short disclaimer. This tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths. So if you see any mistake in my video or see a better way to solve a problem, please add a comment so everyone can learn from you. A few videos ago we learned that in position is a coordinate system in room or world space, measured in pixels. So to create a shader that makes use of that, I thought about a game mechanic where the player character is invisible or undetectable if close to a specific other object. Due to lack of imagination, I'm using some kind of orb object. Of course, you could also use the vertex attribute in position to change vertex position inside the vertex shader, but we'll need to learn a bit more to get some useful shader, but I'll probably make use of that in a later video. Just 2 mentions before we start the tutorial. Shaun Spaldings has a tutorial on outlines which is really great. When you think of it, outlining is very close to silhouetting. His approach is pretty interesting. But I'm going to take an approach where we don't have to take multiple texture samples, but we need to prepare the sprites instead. And GM Wolf has a great tutorial on using in-position simulating waving grass. Although in his tutorial he also uses techniques we haven't learned yet in this tutorial series. Both videos are great and very recommendable. I'll leave links in the description of this video. Before getting started, let's have a look at the sprites I'm going to use to test this shader. Like in the last video, in this tutorial as well I'm using sprite assets from the base project. As background I'm going to use this single sprite background created with a tile set called A Blocky Dungeon by Michele Buchellis. And I'm going to use a character sprite which I created by recoloring Isaiah 658's green cap character. If you're not using the base project, you can find both assets by the links in the description of this video. The last sprite I'm going to use is representing the center of the silhouette effect, the orb sprite. I just duplicated the tileset A Blocky Dungeon and cropped it down to one of the orb thingies there. Now before we start coding, I'd like to explain the 2 major concepts of this shader. The distance from the orb to each pixel of the player sprite to shade the silhouette, and the outline of the silhouette. First, the distance of the orb to the player sprite's fragments or pixels. So this grid is representing our room with the center of the coordinate system in the upper left corner. Mind I said room because all of our calculations in this shader are in room space, not view space. And these are our 2 objects or sprites. The orb, which is the center of the effect, and the player, which will be shaded when getting close to the orb. Now we need to get the distance of each pixel to the orb's center. So we'll pass in the orb's coordinates as a vector to uniform. As you might know, a point in a coordinate system is nothing else but a vector from the coordinate system center to that point. These are the vertices of the player sprite, and as we have learned a few videos ago, their coordinates are stored in the vertex attribute in position. Now inside the vertex shader, we will create a varying from in position, and the GPU will interpolate the coordinates for each fragment or pixel, like so. So the fragment shader can access the coordinates of each pixel of the player sprite in room space instead of in view space, as GLFrag code would do. And again, each coordinate is in fact just a vector from the coordinate system center, but since that's a bit confusing to look at, I'll just represent the vectors of all fragments with one single vector from now on. Now we need to get the distance from the orb to the fragments. And since we're using vectors, we can just subtract the orb vector from the player's fragment vectors. The result will be a new vector representing the distance from the orb to the fragments. And to get the distance, all we now need to do is get the length of that vector with the GLSL function called length. The rest is stuff we learned before in this tutorial series. Now we just colorize every fragment where the equation returns less than the effect distance we want. I know that was a bit of a long explanation of something rather simple, but I think it sometimes helps to see points as vectors, and this was a good place to sneak that concept in. And I hope this will clarify that in position, as a vertex attribute, can be passed interpolated for each fragment to the fragment shader. The second concept is about the alpha value to get an outline. As you have seen in the preview, the shader draws the sprite unicolored when close to one of the orbs in the room. The outer pixels get alpha 1 and the inner pixels are set to alpha 0.5. Thinking about how to determine which pixels stay opaque, I decided to store that information within the sprite. This is the player sprite before any changes. And here's the rules we're going to set up in the shader. All pixels with alpha 0 will stay at alpha 0. All pixels with a pure black color will get alpha 1, which means only the pixels that should get alpha 1 are allowed to be pure black. All remaining pixels will get alpha 0.5. And the result will be this. Now this means we need to prepare the sprites a bit. We need to make sure that only pixels that should have alpha 1 are truly black. First I'll duplicate all needed sprites. I'm using the sprites I named Blue Cap version 1 in the base project assets. And we'll need right walk, up walk, down walk, right idle, up idle, and down idle. I'll also create a new folder named Invisibility Silhouette, move all the new sprites there, and rename them by adding Invis. Now let's open them all up and start preparing them. This is the original sprite. First I'll replace the blacks with another color in all images with the color replacement tool. Then I'll draw every outline pixel as well as the eyes pure black with the bucket and pencil tools. And then I'll replace the temporary color with nearly black, where R, G and B are all set to 1 of 250. And I'll have to do that for every subimage and every sprite. I'll just fast forward through this process. So you see, the disadvantages of how this shader is working are mainly that we need to prepare the sprites and thus have extra work, and we use up more texture space because we have more sprites. The advantages, however, might outweigh the drawbacks. The shader is quite fast and you can determine exactly what is drawn how because we store the exact instruction into the sprite. But now we can finally get to coding. Let's start with the player object. I'll duplicate the template module and name it Object Invisibility Silhouette. In Create Event we can safely remove the region's information and create scrolling mockup. In the region title and so on, I'll add title text and info text. And I'll also disallow deselecting the module. Now the mockup background we're going to use is only 1/4 of the size of the view. So in the region Resize View, I'm going to set the camera scale to 4. And I'm going to create a new region, set sprite and movement type to set up a playable character. Inside that region I'm going to set up a top-down character with the sprites we created earlier. So the sprite blue cap, right idle invis and so on. And as sprite mask I'm going to use the sprite mask of the unchanged character, sprite blue cap top-down mask. The mask sprite, by the way, is just for collisions, not for the shader. And the shadow sprite is just another sprite in the base project's assets. Now since we're scaling the view, we won't need to scale this character anymore, so scale 1 is fine. As is movement speed 1 and image speed 1. And now we can prepare the shader in the region Sprite and Shader. Actually, it's only shader now, since we handle the sprite farther down. So I'm going to remove that from the region title, and I'm going to remove the sprite line as well. I'll name the shader Invisibility Silhouette. And we'll need some uniforms. Since the shader works in relation to the orb object's position in room, we'll need to pass that object's coordinates. So let's set up a uniform handler uOrbCoord. And I also want uniforms to set the size of the effect and the fall-off range. And finally, we need a variable to store the ID of the nearest orb. Let's just start with setting it to no one. The step event will handle this later. The last thing I want to do in create event is naming the sliders of the base project. We'll need one for the range and one for the fall-off, and we won't need the standard slider values to draw. To set the caption, we can use the script slider set caption. And to disable the value drawing, we can use the script slider set draw value. Now the step event. We can delete everything here like in the last video and describe the event as move and find orb. To move the top-down character we set up in create event, we can use the script move character top-down. And we'll name the orb object invisibility orb. So to find the nearest orb, we can just use the function instance nearest like this. This will store the ID of the closest orb or no one if no orb is in the room. On to the draw event. First, let's get the slider values for the uniforms. I want the range to go from 0 to 64 and the fall-off from 0 to 16. So let's grab the slider values and multiply them. To draw the shadow and character, I'm quickly going to grab the draw event from the player template object. Before setting the shader, I'll draw the player's shadow. And after setting the shader, the player. Now we can set the uniforms for the orb in room position, the range in pixels, and the fall-off range in pixels as well. The orb coordinates are in room space since we'll be working with in-position coordinates, hence orb X and orb Y. And the effect radius and the fall-off are in room space as well. If you're not using the base project, just set numbers in pixels here. Now to make sure the game won't crash when no orb is in the room, I'll just put the shader set and the uniforms in an if statement, if orb isn't no one, and end the statement just before drawing the character, so the character gets drawn anyways. By the way, you can reset the shader even if you hadn't set one before, unlike for example resetting surfaces where you need to stick to the stack order. So this code won't throw an error if no orb is around. That's it for the module. The next thing we'll need is an orb object. I'll just create a new object and name it Object Invisibility Orb, and give it the orb sprite. All this object needs is a draw event where we will draw the effect ranges and the orb sprite. I'm doing this in a rather inefficient way here, but this tutorial is about the character sprite and not about the orb. First, let's get the range and fall off again. And then I'll just draw two circles in blend mode add and the orb afterwards. Now for the room. Create a new child of the template room and name it Room Invisibility Silhouette. Inside the room we can hide the tile layer. On the background layer I'll set the single sprite mockup a blocky dungeon. On the main instance layer, I'll place the object Invisibility Silhouette to the entrance of the dungeon. And then I'm quickly placing some wall objects. Now we need another instance layer beneath the main layer. I'll call it Instance Layer Orbs, and place some orbs in it. Keep the orb separated a bit, because the shader we're going to write will only take the coordinates of the closest orb. If the effect size of the orbs overlap, the effect will look wrong. Now we finally get to the shader. Let's create a new shader and name it Shader Invisibility Silhouette. In the Vertex shader, add another varying vec2 VV position. And in the main function, pass the vertex attribute in position to the varying VV position, so the fragment shader will receive an interpolated coordinate. Mind that we just grab x and y of in position. We won't need the z part, but since in position is a vec3 and VV position was defined as a vec2, we need to type the .xy. Also leave VV color in there. In many shaders we don't need it, but in this one we will. Now in the fragment shader we need to grab the varying vec2 VV position. Then we need to grab the uniforms, uniform vec2 orb chord, uniform float invis min range, and uniform float invis falloff range. In the main function I split the glfrag color line again, but for now without the VV color. Now the next line is not absolutely necessary, I just add it in case I want to draw the player character not at full alpha for whatever reason. Since the effect is based on a distance from the player sprite's fragments to the coordinates of the orb, we'll need to calculate that distance. And as we have seen in the explanations earlier in this video, all we need to do is subtract the orb vector from the player vector and get the length of the result. So every pixel closer to the orb object than the effect size should be changed, and every pixel farther away should stay unaffected. But we also have to set up a falloff range. To make that happen, we can take a function we already used before, smooth step. So we create a float weight and use smooth step of invis min range and invis min range plus invis falloff range and distance. Now every pixel within minimum range will be fully affected, and the effect will fall off within the falloff range. Smooth step will return 0 if the distance is smaller than the effect size invis min range, will return 1 if the distance is greater than the effect size plus the falloff range, and will return an interpolated value if it's in between. Now we just need to mix the colors based on that weight. So we're mixing the vertex colors RGB, the base colors alpha, with the base color based on weight. Oh, I forgot to make two changes. First, in the object Invisibility Silhouette's draw event, we can remove the module drawing. And in the room, we can kill all triggers and all but 2 sliders. Now let's run this for the first time. As you can see, when we move into the effect range, the pixels get colored. And we can increase or decrease the effect size with the range slider and the falloff with the falloff slider. But we don't have an outline yet. Everything is at alpha 1. So let's get back to the fragment shader, and in here I'll create a new float alpha. Float alpha is base color alpha times the minimum of 0.5 plus step base color.r plus base color.j plus base color.b, 0.01, 1.0. So we're adding up the color values of each color channel. If that is less than 0.01, the step function will return 0. Else it will return 1. So for pure black we'll get 0, and for everything else we'll get 1. Adding 0.5 to this will give us either 0.5 or 1.5. And capping this at 1 with the min function gives us either 0.5 or 1. although I'm pretty much sure we wouldn't actually need the min function here, because I guess glFrag color will cap at 1 anyways. And multiplying this with base col A makes sure every pixel outside the shape stays invisible. Now we can just replace base col.A in the glFrag color line with our new alpha float. This should get us an outline with alpha 1 and a fill with alpha 0.5. So let's run this again. And as you can see, this works now. But the color is still just white because the vertex color is white. So let's change that. We won't need the shade anymore for this because we use the vertex color to draw the silhouette. So let's just close it and go back to the draw event. In here where we draw the character sprite, we can just replace image blend with whichever color we want. I'll pick the color 720046. Running this again shows our little guy with a purple silhouette now. So that's it for this tutorial about using in position in a fragment shader. I really like how it turned out and I hope you enjoyed this video as well. In coming videos we'll look into other coordinate systems like VV text chord and corner ID. Until next time.